Okay, this is on electronegativity and ionization. This table back here in the back helps to show the sizes of the radius based on their periods and their location on the periodic table. Periods are nothing more than rings, okay? We haven't quite got there with the drawing of the atom, but we are moving that direction. So every time that I go down a period, I'm adding a ring. Now, you can think about this. When you were younger, you might have roller skated. And I remember when I roller skated, we played this game where we'd make this chain. And we'd go around the ring skating. And all of a sudden, the lead person would all of a sudden stop. And then swing around. And what happened to the person on the very end? Well, the people on the end had a harder time hanging on, and sometimes they would go flying off and would end up no longer being a part of the chain. The longer the chain was, the more people on the end would get knocked off from this because they couldn't hang on. The people closer to the person at the front who was in charge of stopping the group, they were more likely to hang on to them. So if we take this idea and we think of the person at the top of this line of skaters as being our nucleus, and everybody else after that being electrons, you might understand better about these rings, okay? So the further away I am from the nucleus, the harder it is for me to hang on to my electrons, which is why the ones on the bottom of the periodic table are more likely to be radioactive, okay? All right, now let's look at the atomic radius. Whenever I am over here in groups 1 and group 2 and group 3, I'm larger than when I'm over here with groups 5, 6, and 7. Okay? Remember, group 8 has no fight in this whatsoever because they're happy the way they are. They have exactly the number that they need. They have a full octet. Okay? Now, fluorine up here is what we call an electron grabber. It's going to grab electrons whenever it can. So when we think about electronegativity, if you can remember about fluorine, the people around fluorine are also highly electronegative. Oxygen is higher on electronegativity than is sulfur. Even though they're close to fluorine, oxygen has one ring less than sulfur. Sulfur has to hang on to its electrons a little bit more than oxygen does, and so oxygen is more electronegative than sulfur is, even though both of them are close to fluorine. Okay? This side over here, when they make ions, their ion is actually smaller than their parent. These side over here, groups 2, 3, and 1, will make positive ions or cations. Over here, groups 5, 6, and 7 will make a negative ion called an anion. Their anion gets larger than the parent does because you've added electrons, and even though we know that they should start pulling in towards the nucleus, those electrons aren't the ones they really were supposed to have, and so they don't quite pull in like they're supposed to, and they're a little bit larger. Let's just leave it at that for right now, okay? So this should help you with the understanding of electron affinity and ionization. Electron affinity and ionization are two different things. Electron affinity is referring to the ability to grab electrons. So this side over here is going to be higher. My positives want to give those up, so its electron affinity is lower. Ionization energy is referring to the ability to make ions. There's also going to be higher over here, okay, because these are obviously going to make ions very readily because they're going to grab electrons, because we know fluorine is our electron grabber, okay? They sound like they're similar electron affinity and ionization energy, but they are not. Electron affinity refers to the ability to grab electrons. Ionization refers to making ions. Yes, you have to lose or gain electrons to make ions. Okay, so they are interrelated, but they are not the same thing. Have a great day.